I'm very happy to introduce Jonathan Leake, who will tell us about Lorentzian polynomials in high-dimensional expanders, trickle-down theorem. I guess I went from the bottom up. All right.
Okay, yeah, thanks for inviting me. Thanks for coming to my talk. So yeah, the main goal of this talk is going to be to discuss trickle-down theorems for high-dimensional expanders. It's a technique for proving high-dimensional expansion, which I'll define all these things in a bit. You know, in order to motivate these theorems, we're going to talk about, while there are many applications of HDX, we're going to talk about one particular application, which is going to be to sampling. Okay, so that will be the motivation. It's going to be efficient sampling. Okay, and in particular, we're gonna look a lot at spanning trees, but we'll talk about something more at the end. And also, if you know what a matroid is, the basis of a matroid, pretty much everything in this first part of the talk also relates to bases of matroids. Okay, so over here I have a graph that I'm looking at, this one, and forget kind of the graph structure of this graph, just look at kind of these nodes here. These are all the spanning trees of this graph, okay? And if I wanted to, say, sample a random spanning tree of this, one thing I could do is I could iterate, sort of enumerate the spanning trees, assign a number to each of them, and pick a random number between 1 and the number of spanning trees, okay? The problem with this is we want sort of these algorithms to be efficient in the sense that hopefully polynomial time and say the number of vertices or edges of the original graph and the number of spanning trees can be quite large. And so enumerating them is already a problem. So we need to figure out something else to do. Okay, so what we're going to do is we're going to instead think of the spanning trees as the vertices of this big graph here. Okay, so let me describe what I've drawn here. So like I said, the vertices are spanning trees. And the edges are given by sort of when there is a way to kind of exchange one edge for another to get between the spanning trees. Okay, so for example, if I start with this one, I want to say travel along this edge. What can I do? Well, I can remove this edge here, and I can add this bottom edge here. And so I have this edge between them. On the other hand, this and this, these two spanning trees, the only way to get between them would be to sort of remove the side edges and add the top and bottom. I have to do two swaps to get between those, so that's why I don't have an edge between them, okay? So this is some kind of like edge swapping graph on the spanning trees, okay? And the algorithm that we would maybe try to use to sample spanning trees coming from this graph, okay, and this is going to be uniform sampling. Most of this generalizes to non-uniform distributions, but I'm going to stick with uniform to kind of keep things simple. So how does this algorithm go? Well, I'm going to start at some spanning tree T0, maybe this one, okay? And now I'm going to choose a random incident edge. Okay, so maybe I pick one of these 4 edges uniformly randomly. And then I'm going to move along that edge. Okay, with, let's say, 50% probability. Okay, so maybe I start here, I pick a random edge, maybe it's this one, and now I say I flip a coin. If it's heads, I move there, and if it's tails, I stay where I am. Okay? And again, if I was doing something non-uniform, maybe this 50 would change. Okay, but we're going to stick with uniform. And so then we would repeat this, I don't know, t times for some t. And then we would output the final spanning tree. So wherever we land after these steps. Okay, and it's kind of a well-known fact that as t goes to infinity, this sort of converges to outputting a uniformly random spanning tree. Okay, so for t very, very large, this process does exactly what we want. Of course, the problem is we don't want to let t be that large. We want t to be some kind of polynomial in the number of vertices and number of edges. So the hope is that we can maybe say, okay, well, maybe we can't get an exact uniform sample of spanning trees, but maybe we can prove something that says if t is sort of large enough, not too big, but maybe polynomial in the number of vertices, that we can essentially get kind of an approximately uniform sample. Okay, so that's going to be the hope here. And how can we actually bound this T then? Well, the way it's bounded is via what's called this.
About step one,
Yes.
when you choose a random incident edge, it's uniform at random.
Yes. For uniform sampling, it's uniform. That's correct.
But don't you get
Your
it?
graph is not.
It's not regular. You will not get uniform distribution, but you,
Okay.
you can fix it.
Yeah.
Just to understand.
You mean because it's not regular?
Because it's not regular, yeah, but
Okay.
yeah,
It's fine. It's fine.
Okay.
there are no more.
Well, then I'll
change a bit to make it.
then I'll say choose a random incident edge with respect to some distribution, depending on the vertex. Yes.
Sure.
Okay, so how are we going to bound this T? Well, the way it's done is you look at a certain matrix, the probability transition matrix of the walk that I just described. It's a random process. Okay, the idea is that, let's say I'm going to use this to mean right, so this matrix will have rows and columns indexed by the spanning trees. This I mean sort of the T1, T2 entry of the matrix. And this will just be the probability in this process that if I'm at T1, I move to T2 in the next step. Okay, and this is sort of like some kind of normalized adjacency matrix. It's a little bit different than that, but it's something like that. Okay. Okay, so this matrix is not symmetric because of these probabilities. The row sums are all 1, but not necessarily the column sums. Okay, but it still has real eigenvalues. And in fact, because these are probabilities, we know at least one of the eigenvalues, which is 1, the all ones vector. And in fact, it's the largest eigenvalue. Okay? And the way that we can prove that this process sort of finishes quickly or gets close to uniform quickly is by bounding the second eigenvalue. So if I have some bound of lambda on the second eigenvalue, which is sufficiently far away from 1, this is going to imply that what they say, that this process mixes fast. Okay? Fast mixing just means that after some polynomial number of steps, we get close to the uniform distribution. Okay? And
It would be good if you call the number of vertices in your original graph a name, like n.
okay.
And then what you want is this T will be polynomial in this little n, right?
So not the number of vertices.
There is
Yes.
There is one.
Yes.
Yeah, if this is n and you want T to be polynomial in n,
That's
and
correct.
this sufficiently close would be 1 minus 1 over poly in n. Right?
That's correct, yes. So if you have a bound here of 1 minus 1 over poly n, then that would imply a bound on T of poly n. That's correct. So this is sort of the thing that we want to prove for the sampling of spanning trees, but also for a general sampling algorithm that comes from this type of process. So we're going to give this a name. We're going to call the graph, if it has this property, a lambda expanded. Okay, there's actually there's usually two definitions that this name can mean. One of them is bounding just the second eigenvalue. One of them is bounding the second and also the last eigenvalue. But for us, just the second eigenvalue is going to be what we care about. So some people might call this a one-sided lambda expander. Okay, this is what we're gonna call this. Okay, and so our goal then is to try to prove this, some kind of bound like this, 1 minus 1 over polynomial, where a polynomial is in n, the number of vertices of the original graph. That's going to be the goal. Okay. Okay, so how are we going to do that? Well, we're going to use some extra structure, and that's what I've drawn over here. Okay, so it turns out that it's actually quite difficult to bound this kind of directly by just looking at this graph and trying to prove some bound on the second eigenvalue of this associated walk. So instead, we're going to try to break it down into pieces in a certain way, which I'm going to describe now. Okay, so what is this now that I've drawn? Well, I've now switched my graph a little bit. I removed this edge because if I tried to draw this for that graph over there, this would get very complicated. So I'm looking at now this sort of simpler graph, and up here I have its spanning trees. So this now has 3 spanning trees instead of the 8 over there. And I've also drawn all of the forests of this graph. So here are the spanning trees. They're the size 3, 3-edge forests. Here are the forests of size 2, of size 1, and size 0. Okay? And the way that I've drawn this, and also I meant to mention these lines are indicating inclusion. That's all that means. So this is included in here and also in here, this edge. Okay? And this picture that I've drawn is more generally, this sort of structure that I've drawn here is given a general name, which is called a simplicial complex. Okay? And all a simplicial complex is it is a collection of subsets of some finite set, which we'll call E, which is downward closed. So let me tell you exactly what that means for this case. So here E, which we'll call our ground set, is the set of edges of this graph. Okay, so there's 4 elements. And here we've drawn all of the subsets of edges that form a forest. Okay, and a simplicial complex should be downward closed, which just means that if I have some subset in my complex, it means all of its subsets should also be in the complex. So anything here, all of its subsets will be somewhere down below. Okay? And in general, when you have a complex, these things which we are calling forests would be called faces. The spanning trees at the top would be called facets. Okay, that's the general terminology, but we're going to mainly stick with spanning trees and forests. Okay, so there's a couple things I want to point out here. The first thing is we can sort of see the walk that we talked about on that graph somewhere in this complex. And again, I'm going to be sort of maybe fudging again exactly the probabilities when I say sort of randomly walk on the lines here, or just I guess forgive me for that. But basically, what do I mean by that? How can we see this walk that we talked about over there in this? We can see it in the following way. So let's suppose I started some spanning tree. I sort of randomly choose some edge to walk down here. Maybe I walk down this one. And now I randomly choose an edge to walk up. Okay? So maybe I walk up this one or I walk up this one. Okay? And the idea is that if I started here and I move to here, there'll be some probability that I stay where I started, and there'll be some probability that I move here, which is exactly one of these trees, which is sort of an edge swap away, right? If I drop this bottom edge and add this central edge. Okay, so the idea here is that this walk that we cared about can be sort of seen in the top 2 rows of this complex. Okay, and this is sort of what's going to be called the facet walk. Okay, but this is right. If you pick the probabilities correctly, this is the same walk that we talked about over there on that graph. Okay, this facet walk I think was originally defined by Kaufman and Mass, but this is what we're going to refer to here. It is a walk sort of starting at the top, taking a step down, and going back up. Okay, so we have this structure that encodes the thing we care about, but now we want to try to make use of the rest of the structure to try to aid us in proving this bound on the second eigenvalue. Okay, so there's a more natural graph, or sort of a simpler graph that appears in this complex, and it comes from the following. If I look at, say I have this sort of trivial thing down here. If I look at the next 2 levels, I very naturally have subsets of edges of size 1 that form forests and subsets of edges of size 2 that form forests. And so if I think of this level as vertices of some new graph, I can then think of this level as defining the edges, right? These are just pairs of things from this level, which naturally defines the edges of some graph. Okay? So there is this graph that can be defined from the bottom 2 levels. We're going to call the base graph. Okay?
Which is complete, right? I mean, if the original graph was simple.
If it was simple, yeah, but we won't necessarily be, in fact, we'll see this graph kind of appear, so that won't necessarily be the case. But yes, in this case it is. That's right. So if this complex was a lot taller, right? We would have looked at the top two rows, we would have looked at the bottom two rows, but there's a bunch of stuff in the middle that we haven't really looked at yet, okay? And there's a lot more structure there coming from this graph. So what we're going to look at now are sort of subcomplexes. So for example, what I've done here in orange is I've picked a particular face in the complex and I looked at everything above it. Okay, so everything that's above this in the complex, I colored orange. Okay? And so this is it turns out, some simplicial complex itself. And in fact, in this case of spanning trees, it has a very natural interpretation. It is related to contraction of edges on the original graph. So if I take this particular thing, it's just one edge, and I contract it in the original graph, keeping multiplicities, I would end up with this graph here, right? I would just be contracting that bottom edge. And if I take all of these orange nodes and I contract that bottom edge, I would end up getting the forest complex of this graph. Okay? So here now I have this new complex, and now I can talk about the base graph for this complex. And so we will also look at that. So I'll say this. Okay, so in the language of simplicial complexes, this subcomplex is called a link, sort of everything above a particular face. And so we could take any face here, corresponds to any sort of number of contractions, and look at the base graph above that particular choice of edges. Okay, and so these are the structures we're going to be working with. This is the structures of something like this that we're going to be talking about. And the idea is going to be that we want to try to relate this bound that we want to get to some kind of eigenvalue bounds on these base graphs. I haven't really defined a random walk in these base graphs, okay? But since this matrix of this walk is related to some kind of normalized adjacency matrix, there's a natural way to define these eigenvalues. And we're going to try to relate bounding those eigenvalues to bounding this one that we care about. Okay, that's the idea. Okay. So now going to define for us what a high-dimensional expander would be. Okay, and throughout I'm going to use the term HQ. Okay, so here's the definition of what is called local spectral expansion. Okay, this definition I think has a kind of a history of how it got built up to the definition I'm going to write down. Papers of Kaufman and Oppenheim, Denner and Kaufman, Kaufman and Mass, and Oppenheim, and sort of leading to the definition that I will now give. I forgot to mention this, we're also going to call sort of the height of the complex the height, and I'll let this letter D denote that. Here it's 3. We have sort of level 0, 1, 2, 3. Okay, so we call a simplicial complex X of height D. An expander with these D minus 1 parameters here be not beta naught through beta D minus 2 if for all k all of the base graphs of height k are beta k expanders. And again, what I mean by that is just, so you look at all of these different base graphs, you can come up with, right, the base graph of the whole complex in this case will be related to beta 0 because it's the base graph at height 0. And all of the base graphs related to things right above each of these will be height 1. Okay, you look at these base graphs, you look at some kind of normalized adjacency matrix, and you want it to be that their second eigenvalue is bounded by this beta k for all lengths of height k and for all k. Okay, and here in particular, right, when d is 3, the number of parameters we have here will just be 2, right? We'll just have beta 0 and beta 1 because 3 minus 2 will be 1. Okay, and so like I said, we hope to bound the second eigenvalue of this base graph by beta 0 and the second eigenvalue of these kind of base graphs above these size 1 things by beta 1. Okay, so how does this help us in our original motivation here? There is this thing called the Leave-Lau theorem, okay, which has also been, there were a number of results that led up to this theorem, okay? But what does it say? It says that if you have a certain type of expansion, then you get exactly what you want. Okay, so if you can show that this definition holds for constant over d for the height 0 things, constant over d minus 1 for height 1, etc., then this theorem says that you can get a bound on this lambda 2 up here, which is 1 minus 1 over polynomial in the size in the height of the complex, which in our case, right, the height will be related to the number of vertices of the original graph. Okay?
What can you repeat? What are the weights that you put on the base graph of when you are at k?
Yeah, so I didn't say, but the idea is that you have some distribution on the facets, right? Maybe it's going to be uniform for us. And so now whenever you look at some link, so I fix this, and now I look at the base graph above that. I mean, we're already at the top, so it's a little bit right here. The weights just end up being right. If you're at the very sort of top of the complex, the weights end up just being the probabilities of the facets from the original distribution. But if you're sort of looking, say, at the base graph above this, then the weights for each of these edges will be somehow the I think it is the sum of the probabilities of the things above it, or
maybe think about it as to sample at level k, I first sample a random top level face and then subsample uniformly at random a k set with that. That'll give you the right distribution. But you can also do it the converse way.
Yeah. Okay.
It's simpler to say.
Okay. Thank you. Yeah. Okay. So we have this definition. If we can prove this type of expansion, we can use this theorem to get what we want. And so our main goal for this talk is going to be how can we actually prove this type of expansion or some type of expansion for a given simplicial complex that we care about. Yeah.
You know, like d minus 2 different bigger terms, and one like as the denominator keeps getting smaller and smaller, it's not going to make sense at some point. Like, do you have some universal constant that's like?
I think universal constant up here.
And it's like min of 1 and that or something.
I think this should just be thought of as a universal constant, always independent of d.
Right, but his point is that at some point it's going to become greater than 1.
Yeah, it's going to become greater
But
than
it
1.
is, it's usually like a min.
So it's
Like
a min of 1 in this.
As long as you have a constant number of levels that are some constant in theory.
Okay.
This here will not be constant level. It's related to the number of edges in the original
No,
graph.
but at the end,
I know, yeah.
Yeah, the denominator is going to be what? 1, 0.
I think once d becomes a constant, like as you walk down this, it becomes constant. You're going to have 10 guys at the end where this bound is trivial. So you also need an additional bound on those guys at 0.9 or something like this.
Oh,
It's
Oh, the-
connected,
Okay. Do you mean this capital O
No, it
one
needs
is
to
something
be
less than one?
bounded away,
binded away even
In
for
some way.
10.
like, but by one minus,
Oh, so
like one over.
so like
volume.
min of 0.9 and that.
Yes.
Yeah.
Okay, okay, okay.
But this is already what you wanted to prove. If you just want the
But these are not the same objects.
No, it's not the-
No. So the height d minus 2 things here will be sort of very small pieces of the thing that we were originally analyzing. Right. For instance, this one only is containing, I mean, this is like a small example, but it only is looking at these two spanning trees as the edges. So somehow in a much taller complex, at the top, you have these very small pieces of the thing you want to analyze. And the hope is that if you can analyze those small pieces and then also all of these kind of pieces from looking at all these different lengths, then you can use that to analyze the original thing, which is what this theorem says. Okay.
Really there. This complex is size exponential in n. And it's the units are linear or network. So it's very fast. The link small. Still very small pieces for expansion on them. And somehow it's size. Makes sense. The piece.
Like in this case, if you look at the top level, there's only finitely many cases for all graphs combined, right?
No.
The top level, the beta d minus 2, there are only so many graphs on 3 vertices.
No, but it will not be straight. It will be some number of edges. M edges.
No, but in the top
Like-
level, you only have
3 vertices, but multi-graphs.
Yeah, but still.
Yeah. So, I mean, in this case, that's right. The analysis, well, as we'll see, somehow like the pieces become much simpler than the original problem. And you're exactly right. It is 3 vertices.
Not constant size, like
Think of
maybe it's a graph on
Oh.
3 pieces, but each piece is large, so there are many edges.
You want to think about this for families of graphs that go to infinity.
Yeah, I was just saying that the top level.
At the top level,
It's only graphs with 3 vertices, multi-graphs.
that's correct. At the top level, it's multi-graphs with 3 vertices. That's correct.
In this example.
Yeah.
In this
Well,
example.
If it was n, it would be n.
No, but wait, it's not, the graph in the link
No, no.
is not a graph over 3 vertices. It just comes from trees and graphs of 3 vertices. So it's not a finite number because you can have many multi-edges
Okay,
between.
Yeah.
okay.
It's not finite, but it is multi-graphs on 3 vertices in this particular example. That is correct. Yeah. Okay, so how are we going to prove this? Well, I'm going to cite a theorem that's typically called the Oppenheim trickle-down theorem. Okay, and I think this is around 14, I think. Okay. For proving some type of expansion for a simpler complex. Okay, and the theorem says if X is connected. Okay, so I haven't told you what this means, but all this means is that if you look at all of the base graphs of all of the links, the graphs are all connected. That's all this means. Okay, if it's a connected complex, such that the top base graphs, so the ones we were just talking about for the spanning tree case, okay, so if you know something about this second eigenvalue for the top base graphs, then you get this more general expansion property. Okay, for some particular number here. Okay, so this is some, okay, so you have to pick some epsilon greater than 0 here and less than or equal to 1. Okay, but for any such epsilon, if you have this type of expansion for the top base graphs, then you get this definition here, where beta k is this. And the only point I want to make here is that if you think about, for instance, what happens when k is 0, you end up getting beta 0 as something like 1 minus epsilon over d minus 1. So, okay, up to, I guess you'd have to make the constant a little bit different, but is essentially constant over d. Okay, and as you make k larger, this in fact improves. So this is going to be even better than this. So usually the hardest thing to prove is that beta 0 is what you need it to be. And then this in fact gets better instead of worse like it does there as k gets larger. Okay? But the idea of this theorem is now we've kind of done a couple steps to kind of simplify what we're trying to do. We originally wanted to prove some good expansion of the facet walk of some complex. This Lev-Lau theorem allows us to break that down to looking at these base graphs. And this now says you just have to say something about the top base graphs. Okay, so in the spanning tree case, like was just being discussed, you just have to say something about 3 vertex multigraphs. And if you can say something good enough for them, then you get this high dimensional expansion, and then it implies a sampling error, or at least an approximate sampling error. Okay, so I'm actually going to make a corollary of this, which is already good enough to be used for the spanning tree example. It's the case where epsilon equals 1. So typically epsilon would be small here, but you can make it as large as 1 and still get a reasonable statement, which is the following. Okay, so if x is connected and the top base graphs are now what? 1 minus 1 over d minus 1 expanders, so that's 0 expanders. Then x is a, again, if I plug in 1 for epsilon, I just get 0 here. Okay, so all of these numbers become 0. Okay, and in fact, by using this corollary, I'm going to talk more about how you can actually apply this. But by using this, you can apply this to the spanning tree case. Okay, and also for if I did a similar thing for matroid bases, if you know what that means. And you can prove that from all this, you get an approximate sampling algorithm for spanning trees over the bases of a matroid. This originally was due to Anari, Liu, Ovescaron, and Vincent about 2019. And this settled this conjecture called the Mihal-Vazirani conjecture about expansion of some graph associated to matroids, the basis exchange graph. Okay, and so what we're going to do now is I'm going to sketch a proof of this, and I'm also going to sketch a proof of the fact that you get this expansion for the spanning tree case. So those are going to kind of happen at the same time. Okay, so to do that, I'm going to introduce the last thing in the title that I haven't talked about yet, which is Lorentzian polynomials. Okay. Okay, so this definition is going to be kind of a culmination of a lot of work of some groups, and I'll mention those groups in just a minute. Okay, so we're going to start with some open convex cone in Rn. Okay, and we're going to look at a homogeneous polynomial. In n variables with real coefficients of degree d. Okay, so you want to think of d. You want to think of d as the same d as the height, and n is going to be now the size of the ground set E. So here, since there are 4 edges, that would be 4. Okay. So such a polynomial is said to be C Lorentzian Okay, if two conditions are satisfied, P and Q. So let me write down, I'm going to be using some notation, which I'll write down over here. So given a vector, I'm going to use this symbol to denote the directional derivative of a polynomial, and it just means I sum from 1 to n the ith entry of the vector, and then the associated partial derivative of the polynomial. Okay? So these two properties are, so let's suppose I apply d of these directional derivatives to p. So each of these differential operators drops the degree of p by 1. So if I apply d of them, this will become a constant. Okay, and I want that constant to be positive so long as these are chosen to be in this cone. And the second condition is sort of more important and a little more complicated. So what I'm going to do is now I'm going to take only d minus 2 directional derivatives of p. That will give me a homogeneous quadratic polynomial. When I look at its Hessian, this is the matrix of second derivatives of the polynomial. Since this is quadratic, this will just be a constant matrix. In fact, it'll be a real symmetric matrix for these polynomials. So it has real eigenvalues. And what we want to know about it is that it has exactly one positive eigenvalue.
We want to with the basis of some for any we want to.
This would be for all choices again in this cone. If that's is that what you're asking? Where should these v's come from?
Yeah.
Yeah,
Wait, so they need to be independent or?
they do not.
I see.
You might have, if they're not, you might have a bunch of zero eigenvalues, but we only care about exactly how many positive eigenvalues we have.
And does it matter if they're unit length or?
No, it will just scale the matrix. Because of homogeneity. Okay. So let me start with an example. Oh, I meant to mention, so this definition has sort of a long history. There was a definition for the positive orth, and it wasn't called this, and it wasn't known to sort of be equivalent to this. That's due to Gurvitz in 2009. There were then two equivalent definitions that I've kind of mashed together, again, for when C is just positive, strictly positive entry vectors, due to Brendan and Hu, and also to Anari, Liu, Oves, Garan, and Vincent. And this definition that generalized to cones first appears in a paper I have with Peter Brendan, but it's a very natural definition of the previous kind of just Lorentzian definition. Okay, so let me give you an example. So if X is this complex we've been talking about, then what we can do is we can define a polynomial. I'm going to index the variables by the elements of the ground set or the edges of the original graph. Okay, I'm going to sum over all the facets of the complex, so the spanning trees. And I'm going to look at a term that looks like this. And just to really make clear what I mean by this, this is just all the product. This term is just the product of all the things in sigma of the associated variables. Okay, this polynomial is Lorentzian, where the cone is just, again, the positive ortho, the set of all strictly positive entry vectors.
This is for any matrix or?
Any matrix, that's correct.
So the phenomenon. For polynomial of this form.
That's correct. So for a polynomial of this form, it's if and only if with matrix. That's correct. Yeah, multilinear or multi-affine or however you want it. Yeah. Okay. But homogeneous, multi-affine.
Also, what was if and only if?
So if you start with a polynomial that's homogeneous and degree at most one in every variable, then the sort of support of the polynomial, the terms that appear, with 0, 1 coefficients, the terms that appear in the polynomial form the basis of a matroid if and only if the polynomial has this property.
This is in the Brandon Ho paper.
This is in the Brandon Ho paper. That's correct. Okay, and also more generally, so for each face, let's say tau, so I'm now picking one of these things. We can also define a polynomial sort of based on tau with the same variables. But now I'm going to sum over facets that contain tau. And I'm going to look at the term where you product over all variables except those in tau. Okay? And this is also Lorentzian with respect to this. Okay, really, I should say kind of like the variables, right? This should just be the variables that appear in this polynomial, but actually this is still fine to say. But really, you would think of this in terms of a cone on the variables that appear in this polynomial.
Oh, does the conditions P and Q corresponding to some definitions of matroids like exchange properties?
Say that again.
This Lorentzian characterizes being a matroid, right?
That's correct.
Does P and Q correspond to like some properties of matroid, like exchange properties?
So in the original definition, in the Brennan and Ho paper, it's hard to say, I would say. I mean, this you can sort of extract from that property in the case where you start off with a quadratic polynomial. So you're not taking any derivatives here, and you have this cone, the positive orthant. This condition down here essentially becomes equivalent. Well, as I've said, this condition will become equivalent to kind of being the polynomial is supported on a rank 2 matroid, which is sort of like a generalization of this 3 vertices with multi-edges. And so you have these kind of parallel classes of elements in this rank 2 matroid. I don't know if I'm going to be able to say something that'll be, too good here. But the idea is that in the quadratic case, it's somewhat easy to see that this is equivalent to being a matroid. Why this more generally is equivalent to being a matroid is sort of harder to see.
But it's induction.
But it is induction. That's correct. Yeah, it's induction. It's just not. It's not immediately clear to me just looking at this why you would get a matroid.
You know, these polynomials have many more.
Yeah. There's a lot of equivalent definitions. Yeah, that's right.
Closure properties like they remain like they are if you fix the variable or if you make a variable 0, I guess.
So maybe we'll get to this, but you're changing the positive orthant to just any cone.
That's correct.
Any convex cone.
Yeah.
Actually. Does this also have like a combinatorial counter part?
In terms of an equivalence, not that I know of. No. Very often we look at very specific polynomials that then happen to have some kind of cone Lorentzian property, but I don't know what the right equivalence thing should be, like what combinatorial condition should be equivalent to some other cone Lorentzian. Like the polynomials we look at are very specific, and I don't think that they will sort of fill the space of polynomials that have that property. So I don't know. Okay. So these polynomials have this property. These I'm going to refer to as the facet generating polynomials. This one is pretty clear that that's what's going on. I have one term per facet, but it's the same here. I sort of have one term per facet of the given link. Right? If that was my tau, then I would have 2 terms, one for each of those. And this is sort of like the facet generating polynomial. In this case, after you contract the edges of tau. Okay.
You want to mention log concavity since you did mention.
I plan to mention it in a minute, but yeah, but this is also very related to log concavity. I wasn't going to say too much about it, but I will mention at least applications to log concavity in a second. But I guess I can say right now that this is also equivalent to the polynomial as a function being log concave on the on the cone C, and also if you take any number of directional derivatives in the cone, that polynomial should also be log concave on that cone C. So that's an equivalent definition of this. But it's also related to log concave sequences, and I'll make a comment about that in a minute. Okay, so how does this relate to what we've been talking about? So the Hessian of this particular choice of derivatives. Okay, so let me just make a comment here. This polynomial will have degree equal to d minus the size of tau. So if I take one of these p taus, okay, and I apply degree minus 2 directional derivatives in this direction of all ones, which is definitely in this cone, the positive orthant, okay, then up to some kind of normalization, this ends up being the sort of base graph P matrix for tau. This probability transition matrix that I talked about before, up to some kind of normalization, this Hessian ends up being exactly this matrix. Okay? And so what this implies, and I'll make a little bit of a comment about this, is that this force complex is a zero expander. Right? The idea is that if you can show that all these polynomials are Lorentzian in this positive orthant, okay, then for every tau, I can look at this particular derivative coming from this Q. I know that this matrix has to have exactly one positive eigenvalue, which means I have a bound on the second eigenvalue of 0, right? That's equivalent to saying that it has one positive eigenvalue. And so what I'm saying is essentially the base graph is a zero expander for every tau, and that's exactly this statement. Okay? Okay. So then the last thing here is I haven't really proven this, right? I kind of skipped around this. I just sort of told you these were Lorentzian, and that implied this thing we wanted. Okay? But how can we actually, how would we go about actually proving that these things are Lorentzian? That follows from following. Okay, so this is a corollary of a more general theorem by these groups. So these same groups I've been talking about, Anari, Lua, Vescaron, Vincent, and Brennan and Ho, from about 18. I don't exactly remember the exact year. Okay, and it says the following: X is connected and this polynomial is Lorentzian for all tau of size d minus 2. Then this polynomial is Lorentzian for all tau. Okay, and so this is sort of like a trickle-down theorem for Lorentzian polynomials. So the idea is, okay, if I can show this Lorentzian property for these polynomials whenever tau is size d minus 2, when tau is size d minus 2, the degree is 2, so this is a quadratic. So this boils down to some positivity condition, and just one particular matrix has exactly one positive eigenvalue, the matrix, the sort of the P matrix associated to these tau. Okay, if I have it just for these top links, then I have it for everything. Okay, and then I can combine this with this to get this corollary that I just erased. Yeah.
In retrospect, does this just follow from the trickle-down theorem of Oppenheim? Or?
So, no, At least not that I see, because this is a stronger condition than just looking at a single matrix. And also, I've given you like a corollary of a bigger theorem. And this is where I wanted to talk a little about log-concavity. This is a corollary of a larger theorem that proves, at the time, proved some long-standing conjectures in matroid theory. And the equivalent question, which I think might have still been open for spanning trees at the time, is that if I count the number of size k spanning trees, so I count like the sizes of each of these rows, those numbers should form a log-concave sequence, which just gives some certain inequalities between these numbers. In fact, it's even stronger than that, but some type of statement like that comes out of the sort of more general theorem that this comes from. Okay, so it is related to the trickle-down theorem. Somehow I've framed it in a way that makes it look like it's kind of coming from that or is related to that. But really, this is coming from kind of a completely different place. And I would even say one of the main original motivations for this definition was to these types of log-concave sequence statements. Okay. But you might say, you might sort of look at this, and if all you care about are trickle-down theorems, you might sort of say, we kind of did a bunch of work and added a bunch of machinery to prove something that was like a corollary of a previous result. And so if really all you cared about, was trickle-down theorems, you didn't care about this log-concavity, you might say that this was a little bit overkill. Okay, but with the last part of the talk, I will hope to show you some example where this theory is a little more essential to these types of trickle-down theorems. Okay.
Is this theorem true for every cone?
No. Yeah, no. In fact, it becomes, when you make the cone smaller to try to generalize to things beyond matroids, it's not really immediately clear what should be said here. There are versions that generalize, but it's more complicated.
What do you think X here is? Any complex?
That's correct. Any simple complex that's connected.
With the fixed dimension, high dimension or something?
That's correct. Yeah, that's correct. Okay. Okay, so to do that, we're going to sort of shift gears and talk about some other complexes.
So while you're erasing this condition where you want only one positive eigenvalue, you associate it with other random walk matrices if you don't take, like if you take other.
You mean things where you're not expecting like zero expansion? Is that the problem you're referring to, or?
So I'm just kind of trying to make sense of like you're looking at these Hessians, along any sequence of vectors in the cone. And
Okay.
I understand if this also has some other meaning if you take different vectors.
So I know there are at least some results that I'm not really that familiar with, but this type of technique will give you polynomial time mixing at the very end, but a lot of times you really want like linear mixing or like linear with some log terms. And you sort of need, I think there's some theory where they use all the directions. I think this ALOV group also does this. They use sort of all the directions in the cone to somehow show that implies this stronger mixing time. But I'll be honest with you, I don't know that for sure. You should take that with a grain of salt. But you could also think of it as if you wanted to look at particular distributions that were given by maybe, I don't know, scaling the variables in a certain way. That would be one thing that you could get from this. But in terms of looking at different directions, that is what we will do coming up. But at least with this example, and for the purpose of doing some trickle-down theorem, not that I know of, except for these things I just said.
But I think maybe just from the scaling thing, you can get you get.
I think that's correct. I think that this is correct. Yeah. So knowing that you can sort of scale the variables by positive numbers and then apply the same type of techniques for each of these, I think that's sufficient for this. Yeah, entropic.
It's like they call it spectral impedance with tilts or something, implies this entropic condition.
I think that this is what I'm referring to. Yeah, that's right.
What is this entropic?
So unfortunately, I don't know too much about it, but it is somehow it's a stronger way to do the analysis. Here, if you run this analysis at the end, this like final lambda 2 bound you get is like 1 minus 1 over polynomial, but the polynomial is like either quadratic or maybe cubic, something like this. But somehow if you know all of these directions and you can apply these same type of techniques, you get this stronger type of entropic independence, something like, maybe you can say more about it.
Fraction of the, like if I look at the operator that like the walk that starts at a k face and walks down to a vertex, it looks at the entropy contraction of this procedure at every length. And if you have this, instead of looking at like variance contraction, which would get you the spectral bound, and having this entropy behavior will give you the log n instead of n squared or something. Somehow they prove this entropy behavior is implied by this tilted.
It's by knowing every scaling and knowing this. Okay, so the type of problems we're going to talk about now are what I'm going to refer to as generalized coloring problems. So we're going to start with a very simple graph that we are going to color the vertices. Okay, so I'm just going to look at a path of length d. Okay, and the goal is going to be to color the vertices subject to certain kind of rules or principles. So the first thing is that every vertex has its own colors. They can be the same if you want, but they can be different. Okay? And each edge sort of determines what's allowed. Okay? So we're just going to be looking at a path for now. We want to color, each vertex is going to kind of have its own set of colors. I'm going to color each vertex with something that out of my set of colors, and each edge is going to have some rules for what's allowed to show up for those two vertices. Okay, so of course the kind of natural example of this would be usual proper colorings. Okay, so each vertex is allowed to be colored by some color, and the edges allow only different colors, right? So I can't have like, blue and blue show up across this edge, but each edge allows everything else to be possible. Here's a more kind of maybe different example than like a proper coloring, but fits into this idea. So I'm going to let the kth vertex be colored by a subset of, let's say, the natural numbers between 1 and d plus 1 of size k. Okay, and what are the edges sort of force? They just enforce inclusion. Okay, so to each of these vertices, I can color them, I can sort of attach to them a set of size 1, 2, 3, and all that needs to happen is that this is a subset of this, which is a subset of this, which is a subset of this. Okay?
So directed constraint?
Yeah.
I guess so, but because I'm sort of labeling these with these numbers, I mean, I guess that's equivalent, but either this should be included in this or this should be included in this, but this is always bigger, so there's no way that that one's going to happen. So just they should be comparable as sets. So, but you could think of it that way. Yeah. But anyways, one way to think about this is instead of thinking of it as subsets, I could think of it as sort of the order in which elements are added. Right? So from empty to 1, I add whatever goes here. Then from 1 to 2, I add a new element. Then I add a new element. I add a new element. Okay. So you can also think of this, at least the sort of proper colorings of the path in this case. You can think of them as just permutations. Okay, of say 1 through d plus 1.
Why d plus 1? You have d vertex.
Because I want to I want this to have some choice. If it was just D, then this would be forced to be everything. Yeah, yeah. Okay. The other thing we could do here is I could add an extra poset structure to the numbers 1 through D, or sorry, 1 through D plus 1. And I could say that, okay, also, these are still going to be subsets of size K, but the elements that get added, they should sort of respect the poset structure. So if, say, 4 is less than or equal to 2, it should be that 4 gets added before 2 does, okay? And if I do this, then, whether or not you've heard of these things, exactly what you end up getting are some subset of the permutations called linear extensions of that poset. Okay? And finally, in general, if you had some ranked poset or lattice, that would also kind of work in the same way. So you don't necessarily have to think of it in terms of like subsets. You could think of each of these being colored with some rank K element so that the things, the thing here should be less than the thing here in your poset or your lattice. Okay. And this includes, for instance, if you know what the flats of a matroid are, you could think of coloring each of these vertices with the flats of a matroid. Okay. You could also think of chains in a modular lattice, which is somehow related to, or a generalization of looking at flags of flats in some vector space. And there's a lot of things that you can fit here you could think of as coloring these vertices. Okay, and so we're going to think about a simplicial complex coming from this, called a coloring complex, where the ground set is the set of vertex color pairs. Okay, so all sort of single ways to color a single vertex. Okay, and then the faces are partial colorings, and then the facets of this complex are then what you would call proper colorings, full colorings. Okay. So I hit 12. How much time can I take here?
5 to 10 minutes.
Okay.
How much do you need?
I think 10 minutes should be enough, I hope. But anyway, I'll speed up. Okay. So what I'm going to do now is to present to you a new trickle-down theorem.
Use the bigger eraser.
Oh, that's a good idea, actually, yeah.
Should be that.
Huh. Should have been doing that the whole time, huh? Okay. Due to myself, Lindbergh, and Ovescaron, the people I listed at the beginning of the talk. Okay. It says the following: if X is a connected, again, this is always needed. Okay. Path coloring complex. So just looking at the path. Such that the top base graphs are now 1/2 expanders then X is a 1/2 expand. All 1/2. Okay, and what does this say? What are the top links for these complexes? Right, so I should sort of pick D minus 2 things that I'm going to fix. So I color D minus 2 of the vertices, and I just look at what are the remaining 2 vertices that haven't been colored. What can they be colored, and how do those things relate?
But here you cannot complete every D minus 2 coloring to a decoloring. Right? You don't have the full.
So I am assuming that you start off with some proper colorings and then sort of filter down what the complex is. So the facets are the proper colorings, and then everything below that will be the complex.
Okay.
Yeah. So I'm going to make a couple comments about this. First of all, this is sort of tight in the following sense. So if I make this a little bit bigger, these numbers, there are examples where these numbers here get very close to 1. So you don't really get any good bound that you would want. And also, if I make this a little bit smaller, these numbers become what you need for the Lev-Lau theorem to hold. So this is some kind of phase transition point or something. This is tight for this condition. You get these constants. As soon as I get a little bit lower, it gets much better, like constant over d minus 1. A little bit higher, and I sort of get nothing. So that's the first thing I want to say about this. The second thing I want to say about,
Sorry to slow you down, but
yeah,
so X is a connected path coloring complex. It means you should have in mind this path of length t, but then the coloring rules are
whatever you want,
whatever I want.
whatever you want. But of course, what you choose, I mean, this is some condition you have to satisfy, but if you can satisfy that, you can choose whatever you
So
want.
what's a good example to have in mind?
So a good example to have in mind is either permutations or the linear extensions. Yeah. So both of those have this property
With the half.
with a half, exactly. Yeah. In fact, for permutations, basically there's a single graph you have to analyze, which has exactly 1/2. And for the linear extensions, there's sort of like 5 graphs you have to analyze, and 3 of them are trivial, and the other 2 have 1/2. So this is somehow very tight for these 2 examples, 2 and 3, at least for kind of the uniform distribution on permutations or linear extensions. You can also choose different distributions. We haven't really explored this too much, but this theory will apply again as long as you can prove this 1/2.
It's a different algorithm to approximate the number of linear extensions of a process.
Exactly. Yeah.
Not the volumes of.
Exactly. Yeah. Exactly. Yeah. There's from the 90s, there's the algorithm to approximately count or to approximately sample linear extensions of a post set using some kind of argument with volumes of certain polytopes. And this would be another algorithm to do that sampling or to do that approximate counting. Which I need to say a little bit more about that because, I mean, it's not clear why actually in this case, this should be enough, right? We can't use a Lev-Lau. This is not good enough for that. But it turns out because of this path structure, you can avoid using that theorem. And this is sufficient in this very particular path coloring case to get you sampling algorithms for these facets. Okay, that's another kind of novel part of this paper. We somehow are able to avoid a Lev-Lau, instead using this path structure.
So if you have all halves there, it doesn't imply anything about the down-up walk, but if
In just from a Lev-Lau, yeah,
but if you're a connected path coloring complex, then you can always do that.
correct. Yeah, that's right. Okay. So then I guess I'm quickly running out of time here. I just wanted to, in a very, very loose way, sketch the proof to sort of show you why this Lorentzian property becomes important. Okay, so the first problem is that everything I've sort of talked to you so far about with the positive orthant and matroids, they all relate to zero expansion. And so just using that theory kind of out of the box is not going to be able to deal with this. Okay, and so the first thing you sort of have to do is use smaller cones. Okay, so we're going to have sort of a cone associated to every tau, which is strictly contained in the positive orthant that allows for more general structures beyond matroids. Okay, and also I'm not going to be able to say anything about this, and I wouldn't have said anything about this even if I had more time. But we also have to generalize these sort of facet generating polynomials I wrote down in a very interesting way, but unfortunately, a way I'm not going to be able to really talk about. Okay, there's some way to generalize that's going to allow us to sort of take advantage of smaller cones and get numbers that aren't zero here. There's something you have to do to kind of to tweak these polynomials to allow that. Basically, what's happening is you're sort of putting negative numbers on the diagonal so that whenever you kind of you can sort of remove that diagonal to get the matrix you want, and by moving it to the other side, this is going to give you some bound that's not just zero, but something larger than zero. Okay, so once you have this, you then prove a version of this theorem that I mentioned before. Okay, in this setting, So now you have this kind of more general, these more general polynomials, these smaller cones. You prove some version of this, which said that we just have to look at the top links to say that all of these polynomials are Lorentzian with respect to these cones. Okay, and now here's where the real kind of problem comes about. So we now have these Lorentzian polynomials, right? And what did we want to do before? Well, what we did before was we had our polynomials. We applied this all one's directional derivative degree minus 2 times, and that gave us this base graph, and we could analyze it in this way. We cannot do that here. This all one's directional derivative, it doesn't give what we want. It has sort of the right support, but the weights on the sort of the entries of the matrix aren't right. So you can't use this to actually analyze what you want. So instead we have to do something different, okay? And it's the following. So we now choose some special vectors, okay? Alpha 1 through alpha d in the closure of the cone, but you can just think of them as basically being in the cone and say maybe with respect to some tau, okay? These are going to be, in fact, let's just think of it like this for now. These are going to be one for each vertex. And the idea is that you can choose these vectors such that when you apply this directional derivatives, it acts, okay, by marginalizing out that vector. Sort of summing over all the possibilities of that vector. Okay? And so we can't just apply this directional, this sort of all ones derivative to get what we want. So instead we sort of have a vector for every vertex. We have some derivative that acts by marginalizing out that vertex by sort of summing over all the possibilities. And then what we can do is we can use now some product of d minus 2 directional derivatives, all of the directional derivatives not coming from these some 2 particular vertices, okay? So we apply this to our polynomial to analyze this pair of vertices. And we do it for all pairs. And then we combine all of this information, analyze the base graphs. Okay, but the idea is somehow there are these very special vectors in this cone. It's not something just like the indicator vector of that vertex or something like that. It has some more interesting meaning, but there are these special vectors that when you think of taking directional derivatives, it marginalizes out that vector. You marginalize out all but 2, it marginalizes out that vertex. You marginalize out all but 2 vertices, okay? And because this polynomial is Lorentzian, the associated Hessian here will have one positive eigenvalue, and that will tell you some kind of eigenvalue bound on something related to these 2 vertices, okay? And with that information, you do this for every pair of vertices, and you combine them. This combining is some linear algebra. It doesn't use anything too complicated, and you can then analyze the base graphs by doing this, okay? So I guess I'll have to stop there. The last comment I will make is that in a later paper with just Cheyenne, we were able to generalize this to all graphs. We don't have a lot of great applications of that, but this sort of idea also generalizes beyond paths. But I would love to know if there's a way to avoid Lorentzian polynomials to do this process, but at least insofar as I can see, I don't know how to avoid it. So anyway, thanks for listening. Yeah.
Thank you. Time for a couple of questions.
Just to understand, this is any graph with any constraints on the edges for the colorings.
Yeah.
Will give you a Trickle-down theorem of this nature.
So in the case of a path, you get this like 1/2 and 1/2. In the case of a general graph, it's more complicated, but at least one thing you can probably say is that it's a little more complicated than this, but this denominator should somehow be related to the max degree of the graph. But yes, there is some general feature.
2 in a path?
In the path, it's 2. That's why you get a 2. Yeah.
Can you say something intuitively about what this theorem means, or some interesting case where you wouldn't expect to have any kind of trickle down, but you still do get it?
So honestly, coming into this, I didn't know much about HDX, so I didn't have a lot of expectations. So I'm not really sure what I would say, other than it seems to me that when people are proving things about expanders, they are expecting something much better than this. And so the fact that this is tight for either permutations or linear extensions, I think might be somewhat surprising, just because you sort of, I don't know, at least all the trickle-down theorems I know get something much better than this at the end. But beyond that, I'm not really sure, what to say. Again, the other thing is, which is kind of also, I don't know how to think about this, but again, if you have like a 1/2 minus epsilon here, then you immediately get something that's basically good enough for a level out. So this is right on the boundary, and for some reason, right on the boundary, you get this instead. And I don't know. Honestly, one of the reasons I was happy to come here is I want to talk to people about HDX, because I'm not really an expert, and I wanted to know what people thought of these things. So I'm not sure if that's a great answer to your question, but I'd be interested to know maybe your answer to the question somehow. Yeah.
Right, maybe we can talk over lunch.
Yeah.
All right, thanks.